In this lesson, we're going to talk about potential energy and potential. Here are the objectives. Just like in the previous lesson on fields, we're going to be focusing on the electric and gravitational situations and making comparisons between the two. Let's start by thinking about work. Imagine I have a large central positive charge here and a smaller positive charge, and I want to move this positive charge, the one on the right, the smaller one, towards the one on the left. I'm going to have to exert a force through a distance because they're going to repel each other. Remember that when I exert a force to move something through a distance, I'm doing work. So I'm going to call this the external work that I'm doing here. And because I'm exerting a force in the same direction as the displacement, that's positive work. So my work external is positive. Also remember, when I do work on something, I change the energy of the system. Now if I'm moving this at constant velocity, the kinetic energy is not increasing with the work that I'm putting in, so the potential energy is. I'm increasing the potential energy, here specifically the electric potential energy, and if I do 10 joules of work, then the electric potential energy is going up by 10 joules, etc. In contrast, imagine I had a central negative charge. Now if I had a little positive charge over here, I wouldn't have to do anything for them to move towards each other. In fact, they would zoom together, and the kinetic energy of, if I imagine the negative one staying stationary, the kinetic energy of the positive one would increase greatly. If I want to keep that from happening, if I want to just allow it to move at constant velocity so the kinetic energy doesn't increase, I actually have to exert a force in the opposite direction. Now I'm exerting a force in the opposite direction to the motion. Again, I'm letting this move to the left with constant velocity. So as a result of that, because my force is in the opposite direction to my displacement, my external work, the work that I'm doing with the hand here, is negative. And so as a result, if the kinetic energy is not changing, I am taking energy out of the system, and that energy is coming from the electric potential energy. So the potential energy of the system is going down as the positive charge approaches the negative one. For example, if I do negative 10 joules of work by exerting a 10 Newton force to the right while the object moves 1 meter to the left, now I've taken 10 joules out of the potential energy. The potential energy has gone down by 10 joules. A similar situation arises if I have a large central mass that I'm going to imagine stays fixed in place, and I have a small mass that I allow to move towards it with constant velocity. Again, if I don't want the kinetic energy to increase, I need to exert a force in the opposite direction. My force and my displacement are in opposite directions, so my external work, the work that I'm doing with my hand here, is negative. And as a result, if the kinetic energy is not decreasing, the decrease is coming from the potential energy. So the potential energy is decreasing as the two masses approach each other. So the work done by the external force, indicated by my hand in these diagrams, is in each of these cases being done against the gravitational or electric force. Here I'm pushing inwards against the repulsion, and here I'm pushing outwards in each case against the attraction. So that work being done by the external force against the electric or the gravitational force is stored as potential energy. The change in potential energy is equal to the external work. And when the work being done is positive, then the potential energy is going up, as in this example on the left. And if the external work is negative, as in the examples on the right, then the potential energy is going down. Notice that increasing the amount of charge on either of these would change the force that I needed to exert, and therefore the work that I was doing, and so the change in potential energy. In other words, if this was a 10 coulomb charge and this was a 1 coulomb charge, moving this charge to this spot here would result in a certain potential energy. But if it was a 2 coulomb charge, then moving it to that spot would, by Coulomb's law, require twice as much force over the same distance is twice as much work, and so twice as great a change in potential energy. So the charge on either of them is affecting the potential energy. Now we're going to do the same kind of thing we did in moving from forces to field strength, where we standardized per unit charge. So we're going to divide out the amount of charge over here so we can talk about the potential energy per unit charge at a spot in space, and that we're going to call potential. So in the electric situation, we're going to take the change in potential energy, and we're going to divide that by the charge on that small charge, this little charge over here. And that's equal to the work divided by that charge. And we're going to call that the change in potential, delta V. And I'm going to put a little sub E here because we're talking about the electric situation. In other words, now I can talk about this spot over here and this spot over here. Let's call those A and B. And now it doesn't matter whether I'm moving 1 coulomb or 2 coulombs, because the change in potential energy per unit charge, per coulomb, is going to be the same between those two spots regardless. And we're calling that delta V. the potential difference. The potential difference just depends on the two spots in space that we are comparing. It doesn't depend on how much charge is on this small charge because, again, we've divided that charge out. And similarly, we can talk about the change in potential energy in the gravitational situation and divide out the mass of the small mass. Again, that's the external work divided by that mass. And we're going to call that the change in the gravitational potential, delta V sub g. You can see if we're dividing work or energy by mass, we're going to have units here of joules per kilogram. Again, we're standardizing or making it per capita like we did with field strength. And over here, we're going to have joules per coulomb. Now, joules per coulomb has a special name. We call that volts. And unfortunately, volts, the unit, has the same symbol V as potential. So you just need to keep that straight. Now notice that both of these are differences in potential, so we're talking about a comparison between 2 points. So we always need 2 points, but if we set one of those points at infinity and make that the reference, so if we set a reference potential of 0 at infinity, in other words, we say if we take the little charge as far away as we can from the big charge so that it's really not feeling any force, then there's no potential energy associated with that. We set a 0 for potential energy at infinity, then we're able to talk about the potential energy and the potential at a point. So again, we define that at infinity, when the two charges or the two masses are infinitely far apart, the potential energy is equal to 0 and the potential is equal to 0 at that point. And using that now, we can give definitions that do away with the delta signs. We say that the potential energy per unit charge is equal to just the potential at a given point. We're talking about at one point, but the implied comparison is always at infinity. And the same in the mass situation. The potential energy per unit mass at a given point is equal to the potential at that point. This can be a somewhat subtle point to understand, so let's unpack this a bit further with some definitions. We're going to look at definitions and formulas for potential energy and potential for the electric and gravitational situations. So again, the potential energy in the electric situation is equal to the work done by the external force, that was my hand in the examples above, in bringing a charge from a potential energy of 0, which we've defined as being at infinity, to a given point. So, for example, if I have a large central positive charge here, and I have a smaller positive charge here, and I've been pushing this thing from infinity, so I've gotten it from infinity to here, and I'm going to keep pushing it until it gets to this point here. I'll call that point A. The potential energy that it will have at point A is equal to the work that I've done in bringing it from infinity all the way over to here. That work has been stored as potential energy in the system, and because I'm pushing it in the same direction of its motion, the potential energy is positive. If instead it was a large central negative charge and I was resisting the motion of a positive charge that moved towards it, I would be doing negative work, and so when it gets to A, it will have negative potential energy, and its negative potential energy will be equal to all of the negative work I've done as this thing moved from infinity to the point A. Similarly, in the gravitational situation, if I had a large central mass here and I was resisting the motion of a smaller mass as it moved towards it, I would be doing negative work, and as it got to point A, it would have a negative potential energy because the work done by the external force in bringing the mass, this should say mass, not charge, that's a mistake, in bringing the mass from infinity where it has a potential energy of 0 to the point A is negative. I'm exerting a force in the opposite direction from the motion. So potential energies in gravitational situations are always going to be negative. Now, in terms of equations, I'm going to give these to you without proving them because it requires calculus, but the potential energy here in the electric situation is equal to K times the product of the two charges divided by R. And a reminder that R is the distance between the center of the two charges in the electric case, and it will be the distance between the center of the two masses in the gravitational case. In the gravitational case, the potential energy has a similar sort of form. It's G, our constant. Instead of Coulomb's constant, we use the gravitational constant times the product of the two masses divided by R. But there's a negative in front because it's always going to be negative potential energy, whereas the potential energy in the electric case can be positive as up here or negative as down here, and that's going to depend on the relative signs of the two charges. Now, in moving from potential energy to potential, again, what we are doing is instead of the total work done or the total energy change, we are thinking per unit charge or per unit mass. So the potential in the electric situation is the work done per unit charge, not the overall work done, not the total, but per unit charge, per coulomb, in bringing a small positive test charge, we're going to specify that it's positive, from infinity, where the potential energy is 0, to a given point. And so our equation for that is just going to be our equation above for potential energy dividing out little q, because we're thinking per unit charge. So it's equal to k times big Q. This is the charge on the central large charge divided by r. And similarly in the gravitational situation, it's the work done per unit mass now, per kilogram, in bringing a small test mass from infinity, where we've defined the potential energy and the potential as being 0 to a given point. And again, our equation is our equation from above, but now dividing out little m. And as we've said, the units in the electrical situation end up being joules per coulomb, which we give the special name of volts to, and in the gravitational situation, joules per kilogram, which we don't give a special name to. Note that potential energy and potential are both scalars, unlike forces and fields, which were vectors. So as a result, potential energy and potential add like scalars. Imagine we had a large positive charge here, and I wanted to know what's the potential at this spot in space around it. And let's say that the answer turned out to be positive 40 volts. Again, what that would mean is it's taking 40 joules per coulomb to bring a small positive test charge from infinity to this spot. Now let's add a smaller negative charge over here, and let's say that if the positive charge weren't here, the potential of this location in space as a result of the negative charge would be negative 10 volts. Again, meaning it would take negative 10 joules for every coulomb to bring a small positive test charge from infinity to here. Now, if I wanted to know the potential at that point in space as a result of the whole configuration of both the positive and the negative charge, I just add these two together and I get positive 30 volts. So it's as easy as that. I add them as scalars. So that's a look at potential energy and potential for the electric and gravitational situations.